Review from last time. So I had a surface, I think where we finished was x, y, and then I drew the surface and made it touch such that the first derivatives were equal to 0 on the plane. So you can always rotate a plane to touch the surface, so that makes things, the computations easier. Okay, and we call the surface z equals f of x, y, such that the coordinate x, it's using x for two different things, but I hope it's okay. So the coordinate on the surface, which I use x to be consistent with the book, is has the graph x, y, f of x, y. So we did that, and then we found the formula for the curvature in the direction of v, which is a unit vector in the plane. And we found that that formula was v transpose, and then the Hessian v, which I'll write out. So it was v, if v has two coordinates, say v1 and v2, okay? That matrix, and then v1 and v2. So I get a scalar, which is the curvature, and then we said that the curvature vector, okay, was this curvature times n. So a few remarks. First of all, if we're just working in the special case where v is in the direction 1, 0, okay, then of course we get kappa equal to the second derivative of f with respect to x, which is exactly the same result that you had from first year calculus. The only difference is, as I did it last time, there would have been a square root of 1 plus f prime squared to the 3/2, but remember we're doing the computation where f prime equals 0, so of course we recover the usual result. So that's remark number one. So remark number one is we recover the usual result. One D result, which is good. Okay, remark number two is we call this thing the second fundamental form, the Hessian here. At least it's the second fundamental form under the assumption we don't get that f prime equals 0. So if f prime isn't equal to 0, we're not on the tangent, touching the tangent, then we'll get a different formula. We'll have to correct it. And what's the correction? By that 1 prime, 1 whatever the 1 plus f prime squared 3/2 becomes in the two-dimensional case. But in the case that the first derivative is 0, this is so-called second fundamental form. So which in the planar case, that is in the, okay, so it's a surface in two-dimensional surface in 3 dimensions, is a 2 by 2 symmetric matrix. Okay, well, it's a symmetric matrix. Okay, so it could be diagonalized. So if we make a change of rotate v appropriately, then I can diagonalize it. And then So this can be diagonalized. It doesn't make any difference, so that means there's some, then I'll get kappa 1, kappa 2. Okay, where kappa 1 and kappa 2 are just the eigenvalues of, just the eigenvalues. So in that case, it's easier to see. After diagonalization, again, you can make V1 sine theta. What did I do last time? Sine theta, cosine theta, cosine theta, sine. It doesn't make any difference. Okay. Okay. So it's kappa 1 sine squared theta, kappa 2 cosine squared theta. And now it's easy to see that, again, as you run around, the maximum will either kappa 1 will be the max and kappa 2 will be the min, or kappa 1 will be the min and kappa 2 will be the max. So this gives you the principal, the eigenvalues are the principal curvatures. So we don't have to do the minimization or maximization problem. And a third point, let's look at this formula abstractly. Okay, if I took the derivative of x, I'll do it over here. Remember, work backwards. We know what the easy case was. So what's the partial derivative of x with respect to little x in this example? The partial derivative of x with respect to little x, okay, is 1, 0, and I'll just f sub x. Simple? So let's compute the rest. So what's all the partial derivatives? So x with respect to twice the lowercase x without the bar. So of course we get 0, 0, f sub xx. And of course, then I'll quickly go through the rest. So this would be xy, would be 0, 0, f sub xy, and last but not least, zero, 0, 0, and then f sub yy. So why did I do that? Because then, okay, we can see what pi should be in general without having to stick to these coordinates. So what is this? This is the partial derivative. In this example, this was the partial derivative with respect to x, okay? Second derivative, first derivative, cross product, and two y's, right? Well, they're not equal. It doesn't even make sense, right? Because this is a, right? This is a, rather, this is a vector, right? So I computed it, and I want to get this. So how should I get f sub xx? Well, it's clearly the information is in the last component. But what does that really mean? It means you dotted with the normal, which was 0, 0, 1. So the normal in this case, the normal unit normal vector was 0, 0, 1, of course. So how do I get the last component? I differentiate and dot with the unit normal. So now we see what the general formula should be. Again, evaluating at the point where the derivatives, first derivatives are 0. And I'll write down the other one in a second. But, okay, so what's the general formula? It's take the partial derivative twice, take the partial derivative twice, take the partial derivative cross partial, and now dot it within. So we knew that, but now you see, of course, you could have rotated, so it puts the whole definition in a geometric setup. It says take the Hessian with respect to x and dot it within. So take the Hessian of the location of the point on the surface, okay, dot it with the normal at that point, and you have the second fundamental form. Okay. Now that I know the second fundamental form, I can find the eigenvalues. I find the eigenvalues, I know the principal curvatures. Now I was asked the day before yesterday, the following very deep question. Okay, so good students ask good questions.
So one question I have.
Okay.
So that formula works not just at the origin point, everywhere.
It works everywhere as long as you put there's a factor missing, which corresponds to the 1 over the square root of, as I said, it's missing if f prime of 0 isn't equal to 0, there's something missing, which corresponds in the classical first year calculus case to precisely square root of 1 plus f prime of 0. F prime squared to the 3/2 power. So some things would be missing when we compute the curvatures. Okay, so there's something missing. Okay, so I'll write it. It's a derivation, but I'll just write it down. That's not the. So what was the question? The question is, okay, let's draw the surface, and I ask you to compute the curvature vector. And if I use this to be the normal, of course, then I get kappa, okay, equals whatever the curvature vector is, kappa n, okay. But this is also a normal. So why not use kappa equal to the reverse? Well, that would switch the signs of the eigenvalues, which would switch the signs of the curvatures. So the principal curvatures are not well defined. You could have used done the whole story with the normal the other way. Right? I switch n to minus n, everything switches sign. So principal curvatures are not well defined. Now, there's two ways. One way to think about it is what we say usually in calculus. You'd say, let's say we're doing divergence theorem. Everybody knows the divergence theorem, Gauss's theorem, whatever. So, and we know that if you're going to use the divergence theorem, you want the exterior unit normal. So we have some way to think of the unit normal, exterior or interior. But how do I know if I'm exterior or interior? How do I know if I'm inside the room or outside the room? Well, I have to know where I am with respect to the boundary of the room. So I need information off the surface. Okay. This is a big deal. Okay, so let's just think about it. Okay, so here's the surface of a sphere. How do I know if I'm inside or outside? Is this the normal, that the normal? You need information. You look around, am I inside the sphere or outside the sphere? So it doesn't use information that's just on the sphere. So in geometry, whatever, in English, probably it's a Korean word. So this would require extrinsic, the prefix in English for outside, like exit, from Greek exodus, in the Bible the same. Okay, X, out, okay. So extrinsic information. So for example, if we had eigenvalues minus 5, 3, so minus 5 would be the smallest, 3 would be the biggest, in this case only 2, right? So minus 5, 3, and you could say, okay, what's a good notion of curvature? And is it 5, 3, or 5 minus 3? Well, you think about it, that's a good question. Okay? Well, you could say, let's take the average. But of course, that doesn't work, because if I take the average, let's not worry about the dividing by 2. That's up to whether you want to divide by 2 or not divide by 2. Okay, okay. But minus 5 plus 3 is, okay, if you take minus 2. On the other hand, this one gives plus 2. So taking the average is no good. So the average has a name. So if we take the average, that would be kappa 1 plus kappa 2, or twice the average, depending on what you, okay? That has a name, and that's a scalar, okay? And the book uses capital H, so that has a name. So H is called the average or mean curvature. Okay, and lots of PDE people work on problems which discusses flow by mean curvature, has mechanical meaning, but from the geometric point of view, mean curvature isn't so great, because again, it's extrinsic, because it depended on this sum. We could have gotten, as in the example, minus 2 or plus 2. So mean curvature is also extrinsic. So by this time, you probably figured out the right answer. So it's not adding them together, it's multiplying them together. Because what happens in this example when you multiply them together? Minus 5 times, either way we get minus 15. Simple example, but exceedingly deep, because it means it didn't change with respect to the orientation of the normal. So it's not the sum that's the good guy. It seems it's the product that's the good guy, which is kappa 1, kappa 2. And this one we'll show is intrinsic. In exactly the same inside, right in the surface. It doesn't use any information out of the surface. So the usual story is that if an ant is walking on the surface, the ant will be able to compute enough information to know the Gauss curvature of the surface. Kappa K is called the Gauss curvature. Well, the ant could never compute enough information. There's not enough information, because the ant would then have to get off the surface to compute the mean curvature. So for those of us walking on the earth or whatever, working on a surface theory, okay, you don't want, if you're developing a theory of surfaces, everything should be expressed in intrinsic information and not extrinsic, because extrinsic means you have to know information off. So intrinsic becomes the crucial story here. So now I can, now that we define the curvature story, okay, let's go back. If I already told you something, what's the second fundamental form? Not force, form. Why am I saying form? Form, okay. I better tell you what the first fundamental form is. Now, if this was a course in some other subject, we might have the first fundamental form, the second fundamental form, the third fundamental form, and we could make a whole list. But fortunately, geometry is very good. There's only two, because the third really only depends on the first and the second, and that's the end of the game. There are no higher fundamental forms. So fortunately, it's only one, first, second, and the end. Okay. And that's true in any dimension. It's 1, 2, and finished, which is very nice. Okay, so let's erase and get on to what's the first fundamental form. Since I introduced the second fundamental form already. Oh, by the way, what's the Gauss curvature of a sphere? Let's do one example. It's easy. Okay, so you already know the answer. So if I put a sphere that's x, y, and z. So I won't, not without formulas. Okay, what's the Gauss curvature of a sphere? How did I compute the curvature to start off? I said, oh, let's take a slice and see what the curvature of that curve is. But if I take any slice, it's a circle. So every slice is a circle. So if the sphere had radius A, then the circle has radius A. So every slice is a circle of radius A. So if the sphere had radius A, the circle had radius A. Okay. What's the curvature of a circle? So the curvature of a circle is 1 over A. Okay. So that's very nice. So I know every slice will give curvature 1 over A. So it doesn't make any difference which slice here I get. I'll always get 1 over A, 1 over A. And the product of 1 over A and 1 over A is 1 over A squared. So it's 1 over A, 1 over A. So the two principal curvatures are equal. And their product is 1 over A squared. So we know the Gauss curvature of a sphere immediately. So this is the Gauss curvature of a sphere. So at least we can do one example with no work. So now let's go to more general coordinates and talk about the first fundamental form and then put everything together. So this section 2.2 is called Coordinates, Length, and Metric. So if I can get the paper. Okay, let's pick an example. So if I want to say points on the sphere again. So let's look at points on the sphere. So I take a sphere and I put it at the center at the origin this time. I won't do any curvatures for the moment. So I take a sphere and I put it at the origin. And everybody knows if I do x, y, z, okay, it has radius a, okay? Everybody knows I could, in x, say, as I wrote a function, I could do x, y, z of x, y, and z of x, y is such that x squared plus y squared plus z squared equals 1. So that would give the points on the sphere. But you see it's rather unpleasant, because then if I want to write it as x squared plus y squared, and then I'd have to take the square root. And I have to make sure I take either the positive square root or negative square root, wherever I have to worry about the half sphere and upstairs and downstairs. So rather, as we know, it works, but it's not very pleasant. Okay, so what do we do often is we say, okay, we'll write the points on the sphere in spherical coordinates, and we get a sine phi, cosine theta, a sine phi, sine theta, and cosine phi. And that would be the theta goes this way, and the phi goes that way, and we're on the sphere. So that's spherical coordinates. So what's the point? Okay, this is just an example that on a surface, okay, there are many possible coordinate systems. Here was one. We could have used x, y, z, or I could have used spherical coordinates, which was you give me x and y, and then I have z of x, y. But I also could have theta and phi, and I'd have this one, which depends on phi theta. So I could have used x and y or phi and theta. So we want a theory which is independent of coordinate systems. So that's the motivation. So these are called local coordinates, okay? Because it only may work on a local patch, but in this case they're global except where things aren't defined. Okay, but otherwise everything is okay. So how do we do that? So let's write our local coordinates. Here there were two local coordinates, right? That gave us two local. Right? So when we're doing our story, let's erase the example and start now that we want a theory which is based on, at least for the beginning, two local coordinates. Of course, once you see two, it doesn't make any difference. Two is just make life simple and intuitive. So let's have our surface. And the first thing since I'm interested in length, okay, let's pick any local coordinates you want. So first let's do, just again to make it clear, if I take, as I did it already here. So let's do x and y for starters. So if I want to know what's the length going along the surface there. Okay, so I have to do length. So that means over here, so this, right? X and y are changing, parametrized by some x, y, or even t. Right? So how would we do it? We say length is by Pythagoras the integral, if it's parametrized, say by t, then it's the arc length formula, the s dt dt. Not very deep. Okay, but we know s, the s dt is the magnitude that we call the velocity, which is the x dt. So now x was a point on the surface. So dx dt dt. Okay, t1 to t2. Not very fancy. But now, remember that I wanted x to be a function of the local coordinates. So this position x in three-dimensional space is a function of the local coordinates. So it's the vector x is a function of the local coordinates u1 and u2. So as t changes, u1 and u2 change. So as we move along the curve, x of t, x changes through the local coordinates, u1 of t, u2 of t. So in the simple example, the position on the curve on the surface changes as we move along some curve here. It didn't have to be a straight line. Okay? Okay? So this tells me as I move here, oh yes, u1 changes, u2 changes. Say x of t, x of t, y of t changes here. Hence I know how the position there changes. Okay, but what's that equal to? Well, let's write it out. So by the chain rule, okay, this is what? So this is the x, the u1, the u1 dt. So that's just because u1 is only depends on t. Okay? Plus the x du2 dt. dt. And then I have to integrate from t1 to t2. Okay, so this would be, so what's, if this is, now I know that this is, actually I can move the dt outside. So if you want to think about it, okay, here's the dt. If you don't, no bar underneath, it's scalar. So it's a vector, take the magnitude of the vector. So now I know ds. That's the point. We make the identification. So we see the, in terms of the local coordinates, we see the increment of arc length. So we found, which you probably would have guessed anyways. What is the s? It's the magnitude, the x, if you allow me to use differentials, du1 plus du2. So now I see the increment of arc length in terms of the arbitrary coordinates u1 and u2. So it didn't make any difference if it was xy or phi theta. Okay, we have a general formula. Well, that's a little hard to do business with, but it's much easier to write the square. So I have to take this vector and dot it with itself. So it's a vector dotted with itself. And that's how I find the magnitude of a vector. And let's write it out. So I'll erase everything here. So if I don't make a mistake, let's see, it's ds squared is, its first term is with the u1 squared, so it's dxu1 dxu1. Then the cross product term, you get a 2 dxu1 dot dxu2 du1 u2, and then we get the last term dx u2 dx u2 dotted with u2 squared. Okay, so now we have to make up the notation. So the notation is two choices for these guys. So first, the old notation, which is in the very introductory books. They use the alphabet, Latin alphabet, A, B, C, no. D, well, D, not so good. E, F, G. So that's the classical and my guess is, I don't know, I haven't ever looked. My guess is Gauss used the German letters E, F, G, or maybe with German Gothic symbols. So my guess is Gauss used the E, F, G, so people use the E, F, G ever since. So that's, I think, so that's my guess is, that's how Gauss did it. But more modern notation is we use tenses, but for now just think of them. Don't worry about the tenses. So this is G11 to G12, which is plus G22. So G is the metric. It's a way to get length. So G, which is 2 by 2 matrix, okay, in our case, okay, 1. There's G if you want to think of it that way, okay. And so G is, and it's symmetric because it didn't make any difference, 2, 1, 2, because it's the same thing. So G is symmetric, and so this is called the metric. G. So what's the point? So G tells us how to find the arc length. It says ds squared is, then you'd have to write it out. So I'll write it. So it'd be the sum on ij, gij, dui, duj, where j runs from 1 to 2 in this case. Well, why is that? Well, when I equals 1, we get the g11 u2 squared. When I equals 1, j equals 2, we get the cross product term. But when j equals 2, I equals 1, we also get a cross product term, so we get the 2. And when j equals both 2, we get the u2 squared. Now, there's one painful process, okay, which Einstein realized, okay, to simplify the notation, okay, which you may or probably have seen, is too many sigmas. So we don't use sigma, okay, because we know that if the indices are repeated, we sum over repeated indices. So in geometry papers, books, physics, always the same. some over repeated indices. Saves a lot of paper, saves inks, it's good for the environment. So we don't need to, and too much writing. Okay. So let's do an example and find the, so the example I'll do again is the sphere. So it should be clear. Now if you could remind me what the formula, I'll look because I always get the sines and cosines messed up. So let me write down the formula for the sphere. The sphere was sine phi cosine theta. Go back to what I did before. So x equals a sine phi cosine theta. If I don't make a mistake. Here I have sine phi, a sine phi sine theta. And the last one is a cosine phi. I hope that's what I wrote the first time. Okay, so what does that say? So let's see. So this was, how do I find, so I have to compute the partial of x with respect to, did I do it right? I hope so. Okay, so u1 was, which one do you want to be? Here I have u1 equals phi. So let's do u1 equals phi. Doesn't make any difference. u1 equals phi, and u2 equals theta. So the partial of x with respect to u1 is the partial of x with respect to phi. And if I don't make a mistake, which is always risky, it's a cosine phi cosine theta, a cosine phi sine theta, a with a minus sign sine phi. And now I have to compute the partial of x with respect to u2, which is the partial of x with respect to theta. Okay, so now if I don't make a mistake again, so the derivative of the cosine is minus the sine, so it's minus a sine phi sine theta. The derivative of this one gives a cosine theta. It's a sine phi cosine theta. And last one is 0. So let's see if we can do this without making any mistake. So let's do it over here. So what's the, how do I find G11? That means I have to take the dot product of U1 with U1. So U1 with U1 is this one with itself, gives A, so U1 with U1 gives, let's see, A squared, just square everybody. So it's A squared cosine squared, cosine squared phi cosine squared theta, right, plus A squared cosine squared phi sine squared theta. And the last guy is A squared sine squared phi. Okay, so this is the same, so these two just give A cosine squared. And A cosine squared phi plus A sine squared phi is A squared. And let's do U2 with U2. That one's also easy. And we get A squared sine squared sine squared. And A squared sine squared cosine squared. And 0. Well, this one, it's sine squared plus cosine squared, so we just get a squared sine squared there. So we found for on the sphere, so arc length on the sphere, the s squared for the sphere, we can plug it in. We know the first guy, it's a squared, and that would have been the u1, but u1 is phi, so it's a squared d phi. D phi squared. Okay, and the last one I know is a squared sine squared phi d theta squared. So the only one that's missing is the middle one. So let's do the middle one. Well, we have to take the dot product. Well, the n ones give 0. This one gives cosine, cosine, sine, sine. And we get cosine, cosine, sine, sine, plus minus 0. So the middle one is just... Okay, so what's the point? The one point is, in taking these, when we teach these courses or something, we have the students memorize these terrible formulas. And of course, you don't have to memorize. You can derive it. It's almost easier to do the derivation from than to remember the formula. And the derivation is not that bad. In fact, what is this? Really, this is, of course, just Pythagoras, right? Pythagoras. Huh? It's just a generalization of Pythagoras. So that's the example. Now, I told you that we're missing this factor in front when we do the second fundamental form that corresponded to the 1 plus phi primes f prime squared to the 3 halves in the denominator. So what's the right formula? So I did coordinates, length, metric. Oh, what's the metric? The metric is the first fundamental form. So the first fundamental form is the metric, okay, which is the s squared. So we had I wrote it out, so I don't have to write it again. Didn't I have it here? Okay. Oh, yeah. So the s squared in fancy notation is that. So this is this is the first fundamental form. So in modern notation, the first fundamental form is the metric, or in Gauss's classical notation, EFG, the triple EFG, gives the first fundamental form. So we did first fundamental form, second fundamental form, no other fundamental forms, third fundamental form, that adds no new information. So they mention it in the books, but it's a waste of time. It's just an exercise to convince you that you don't need to go any beyond the first and second. We're doing for time, 10 more minutes. So let's do the definition, because I've been, what happens if you pick a point where the first derivative isn't equal to 0? Not a point of tangency. So what's the right formula? General. Okay, so everything was right. Okay, so it was we knew it was the Hessian. In fact, it was the Hessian, not with F, with the X. Okay, dotted with N. So that part was clear. The question is what's missing in front? And the answer is it's the inverse of G. Now, in this case, G, the scalar G, okay, I have to get it right, yeah. The scale is it's I have it right. It's this. I think it's, I have to remember, but it's the scalar G, which is the, I have to think about a second fundamental. I didn't bring the, let's see. If I have to remember, but I think here the G, okay, with this G denotes the determinant. So you have to divide through by the determinant. Okay. So G is the determinant. Take the inverse, just 1 over G, and multiply. So we keep the same directions. It's only getting the scalar right. Okay, let's think, how is that? I can think about it from the, but okay, I'm 99. I forgot to check, but as I remember. So it's 1 over the determinant, and then this one. So the direction only changes. Okay, so if we pick a point where Gij, okay, is the identity, then the determinant, of course, is 1, and that's where we get the right formula. Okay, so I did that. Okay, so what's the formula in this way? So I gave you before what was the Gauss curvature and the mean curvature. So the things stay the same. Before, the Gauss curvature was, oh yeah, that was the product of the eigenvalues. Okay. But what's the product of the eigenvalues of a matrix? Product of the eigenvalues is the determinant. Okay. What's the sum of the eigenvalues? That's the trace. So now we have the mean curvature and the Gauss curvature well defined, even with G there, and we don't have to do any special thing. So we have the Gauss curvature, capital K, Gauss curvature, mean curvature. Very nicely defined in terms of nice, simple, linear algebraic concepts. Now, the issue would be, okay, which of course is, okay, so Gauss understood everything perfectly well for surfaces. But then you go beyond surfaces, you can get to hypersurfaces, or you can just get to arbitrary guys where you have a metric, okay, and you still want to define Gauss curvature, mean curvature, and other concepts of curvature. Well, this was a big advance in the history of mathematics. So, but Gauss was a smart guy, and he had a smart student. So the generalization, as I said, went from Gauss to his student, Riemann, who generalized everything. So Riemann generalized everything, with a essential guy just becomes defining metric. So let's see if I should do one other thing, some formulas which you can do. Which is the so if I want to know the principal curvatures, okay, so the Gauss curvature just gives me the product of the principal curvatures. Think about it for a second. The Gauss curvature, and then I'll stop. So the Gauss curvature okay, is the product of the principal curvatures, right? You can do the computation for yourself. H is either the divide by 2 or not, okay, is the sum. So you can eliminate, so given K and H, given kappa 1, kappa 2, you can find K and H. Well, you can invert. Inverse problem. Inverse algebraic problem. So given K and H, you can find kappa 1, kappa 2. Not very deep, okay, but there's a formula. Okay, it's solving the quadratic equation. So it's h plus or minus h squared. So kappa 1, 2 is h squared minus 4 kappa over 2. That is just use quadratic formula. Okay, so I could write down examples, but I think this is all so far so easy. So I see it's 1 minute to go, so maybe this is the perfect place to stop. So next time we get to the ODEs and PDEs of geometry, which is the whole idea of the lectures anyways. So that's next Monday, 10 o'clock. Very well.